Everyone, welcome to 21 EC402 Microprocessors and Microcontrollers, and this is Unit 1, the 8086 microprocessor. I am Manimiglai, Assistant Professor ECE from R.M.K. CET. So in the previous lecture we have seen the instruction set of 8086. We have discussed only data transfer or copy instructions and arithmetic instructions. In this video we shall see the logic instructions and shift and rotate instructions of 8086. So now we shall start the lecture. Logical instruction. So the logical instruction available in 8086 are logical AND operation, logical inclusive OR operation, and logical exclusive OR operation, and logical NOT operation. For AND operation, A and D is the mnemonic. For OR operation, OR is the mnemonic. For exclusive OR operation, XOR is the mnemonic. And for NOT operation, NOT is the mnemonic. So, logical AND operation is the multiplication in bitwise, and logical inclusive OR operation is the addition in bitwise. Logical exclusive operation for the function when we have got two inputs A and B, the exclusive OR output will be A bar B plus B bar A. And logical NOT means we are complementing each and every individual bit present. So the format for the AND operation is AND destination comma source. So the content of the destination register or the location is ANDed with the source content, and it is stored in the destination register. So almost all the conditional flags are getting affected after executing this instruction. For this format is AND BL comma CL. So here BL is the register holding some data and CL is the register holding some data. So the content in BL and CL are logically ANDed and the result is stored in the BL register. And the next logical instruction is OR. The format is OR D comma S. So the content of the source and destination register are logically added and the result is stored in the destination. Similarly, like AND instruction, most of the conditional flags gets affected upon executing this instruction. So the example is OR AX comma BX. So BX is a register containing a data and CX is a register containing some data. So here both are logically ORed, which means the bits are added in bitwise manner and the resultant is stored in the AX register. And for the XOR operation, the format is XOR destination comma source. So the content of the destination register and the source register are performed with exclusive OR operation and the resultant is stored in the D register, so destination register. So the example is XOR AX comma BX. The content X and BX are performed with exclusive OR operation. Result is stored in the AX register. Almost all the flags get affected, that is all the status flags are getting affected upon executing this instruction. And NOT operation, the format is NOT space D. D stands for destination. So you can see the operation. D bar is stored in T, which means the individual bits of the content are being inverted and stored in the same register. The format example is given by not AX. The content present in the AX register is being inverted and stored in the AX itself. Upon executing this instruction, none of the flags gets affected. Shall see some examples. So here the destination and the source could be a combination of register and register, register and memory, memory and register, register and immediate data, memory and immediate data, accumulator and immediate data. So these are the possible combinations which we can use for the destination and source for logical operation. We shall see the logical instructions with the help of some examples. So first instruction is AND instruction. So AND instruction can be used in any addressing mode except the memory to memory and segment register addressing. So AND is majorly used for clearing certain bits because AND operation is logical multiplication. So for the multiplication operation, if both the inputs are high, then only the output will be high. At least if one of the input is low, the output is always low. So based upon this logic, we can use it for clearing certain registers. So here you can clearly see an example. So the first input is don't care conditions, that is AND with 4 zeros and 4 ones. So if one of the input is certainly low, the output is low. So the AND operation of these two will fetch you the first 4 bits, that is the higher bytes, higher nibble to be all zeros, and the lower nibble would be of don't care condition since we have got all ones in the lower byte. So similar examples have been presented and BL, 0FH. So 0FH is the immediate data that is to be ANDed with the data present in the BL register, which is of 8-bit size. The next example would be AND AL, 345H. So this 345 might be a memory location. In that memory location, you may have a content or operand. That operand has to be ANDed with the data present in the AL register of 8-bit size. Then moving on for the OR instruction. So OR instruction is used for setting certain bits. So OR operation is the logical addition. So the operation is that whenever at least one of the input is high, the output is always high. And get most of the bits to be set, that is most of the bits to be 1. So here an example is presented. So one of the input is don't care, that is it may be 0 or 1. That content with 0F, that is higher nibble all zeros and lower nibble all ones. So for the first 4 bits, don't care with 0, whatever the value in the don't care, maybe 0 or 1, that will be reflected. For next bits, lower bits, you have all ones. So if it is all ones, the output is always 1. So we are getting the output for lower nibble as 1. So it is used for setting the upper 4 bits according to this example. Now this is the XOR operation. So it stands for exclusive OR operation. If the inputs are different, the output is high, which means if one of the input is 0 and the other input is 1, the output is 1. For the same inputs, the output is low. Output is high when we are getting different inputs. So here we have got a number for the input 1 and the other number for the input 2. So here you can see 1010 and 0011. It has to be XORed with 0000 and 1111, which means 0F is XORed with A3. So the output will be, if you are performing in bitwise manner, LSB and LSB, you can start to compare. So 1 and 1 will be getting 0 because of the same inputs, and 1 and 1 for the next bit it is 0. Here the another two bits are different. The first input has got 0 and 0, second input has got 1 and 1. So it is 1 1 different inputs. And if you apply similar logic for the higher nibble, the output will be 1010. So this is how an XOR works. Some examples are presented. So AND CL, 0FCH. So this is for AND operation. And OR CL, 0C0H. So these and all 0FCH and 0C0 are the immediate data. Then XOR CL, 020H. So this is also an immediate data that has to be XORed with the content of the CL register. Next instruction we have is the test instruction. So test instruction is used for the AND operation, but the data will not be stored in the destination register. It only perform AND, and the output content will not be stored in the destination byte, but only the flags are updated according to the output. That is the logic for test operation. Then we are moving on to the next set of instruction, that is shift and rotate instruction. So we have left shift and right shift, left rotate and right rotate. So there are two different categories of shifting. One is arithmetic shift and another one is the logical shift. And two categories for rotation. So rotate left, rotate right, and rotate left through carry, rotate right through carry. So these are the different shift and rotate instructions available in 8086. Now we shall see what is the format, mnemonic, and how it is being executed. So the shift instructions. Shift instructions operates in arithmetic and logical manner. So for left shift we have shift arithmetic left SAL instruction and shift logical left SHL instruction. And similarly for shift logical right we have SHR and shift arithmetic right we have SAR. So for any shifting operation to occur, first we have to set up a count, and for that number of count times the shifting operation is going to take place. If my count is 1, so one time the content will be shifted. That is the logic it works. Now see for example for the SHL. So here AL register, the first example we can see SHL AL, 1. So AL is the destination and 1 is the count. So the content of the AL will be 1 bit shifted left, and at the last right will be including the zeros. The vacated position will be filled with zeros and the result will be stored in AL itself after one single shift, because the count value given as 1. So upon executing this instruction, most of the flags are undefined. We need not to bother about the data in the flag. And SHR is the shift right. So shift right happens with the same. So we have to specify a destination with the mnemonic SHR and count. And shift arithmetic right is also with the same format. Here, arithmetic shift means we have to preserve the MSB. So let us see with an example. So first let us understand what is logical and arithmetic shifts. So logical shift will shift the bits to the left or right without preserving any of the bit. So the bit will be directly positioned to the next left or right according to the right or left shift. But in case of arithmetic shifts, we have to have the sign bit preserved. That is, the MSB of the bit has to be preserved and it is not vanished once the shifting operation occurs. It has to be in the position. So here you can see shift left operation take place from the LSB to the MSB, and shift arithmetic left also same. From the LSB the bits are moved to the next bit position through the MSB. For shift right operation, what happens? From the MSB it is moving towards one bit towards the LSB, and for shift arithmetic right the MSB will be maintained as a sign bit and it is positioned in the MSB alone. So for SHL instruction, it performs logical left shift on the given destination operand. So filling the lowest bit with 0. So whenever the data shift to the left by one position, 10 is inserted at the LSB for the first shift. For the second shift, 2 zeros will be inserted. Likewise, for how many number of counts, that times of zeros will be inserted, and the bit positioning will be one bit forward towards the MSB. And SHR instruction. So here also the same content. Here the MSB will move one bit on the right hand side. So LSB gets vanished first and zeros will be positioned at the MSB for the first shift. For the second shift, 2 zeros will be inserted along the MSB position. So shifting right by n bits will divide the operand, the content, by 2 power n. And for shift arithmetic right instruction, the MSB is preserved. So whatever the value is present in the MSB, that has to be maintained in the MSB itself. Then we move for rotate instruction. So ROL stands for rotate left, ROR stands for rotate right, RCL stands for rotate left through carry, and RCR stands for rotate right through carry. The format is ROL D, counts. Here the data present inside the register or the data available in the memory location are rotated from LSB to MSB in a rotating manner. So based upon the count specified by the user, that many number of times it is going to be rotated. So the carry flag and overflow flag are undefined if count is not equal to 1. Format is ROL destination count. So destination could be any register. So here ROL AL 1 means the content present in the AL register are rotated through left direction for one time. And similarly, rotate right takes the example RO or AL 1. So here the content of the AL register are rotated towards the right direction for the single time because the count is equal to 1. In similar way, if you include a carry and rotate, then it is rotate with carry. If you include the carry flag and then rotate the content, it is called as rotate with carry. So it is, if it is happening in left direction, it is called as RCL, that is rotate left through carry. And it happens in right side direction, then it is called as RCR, that is rotate right through carry. The same format is applicable for the 4 shift and rotate instructions. So here you can briefly see the rotate left instruction. So rotate left, rotate shifts one bit at a time to the left. Okay, so the highest bit is copied into the carry flag, which means the MSB is copied into the carry flag, and the lowest bits are moved to one position left, and here no bits are lost and no zeros are inserted. So all the bits will be in form of rotation. It is present within the register specified. So here you can see the example, move AL comma double one double one double zero double zero B. So the input data is in the form of binary format. So if you are going to left rotate the content of that AL one time, here you can see the MSB1 gets occupied to the LSB and the bits are moving one bit left. So it is called as rotate left instruction. Rotate right instruction. So here the LSB is moved to the carry flag and also copied to the MSB, and it is rotated throughout. So the lowest bit is copied into both the carry flag and the MSB. Here no bits are lost and no zeros are being inserted. So take for an example, move AL comma double one double one double zero double zero B. So rotate AL comma 1. So you have to rotate this in the right for one number of time. So what happens? Your MSB is moved to the your LSB is moved to the MSB, and the remaining digits follows in the right side direction. So your output in AL will be this LSB 0, that becomes the MSB, and all the bits are moved one position towards its right. So your AL output will be 0, 1111, 000. Similarly, we can apply the same logic for move DL, 3 FH and rotate right the content of DL for 4 times. So if we rotate means what happens? Upper nibble will become the lower one and lower will be becoming the higher one. Okay. So this is how this works. Then RCL, rotate through carry. So here the content of the carry flag is also included, and then the bits are being rotated either left or the right direction. Okay, this instruction is used for shifting each bit to the left, and also it copies the carry flag into the LSB, and the most significant bit is sent to the carry flag. So it works in the different manner than RO or instruction. So we have seen all the rotation and the shifting operation for 8086. Thank you.